Hello students, welcome to EPG Pathshala. I am Dr. Aranya Bhattacharjee from the School of Physical Sciences, Jawaharlal Nehru University, New Delhi. Today we are going to discuss about a module, Electron in Periodic Solids Tight Binding Method under the paper Solid State Physics. Learning outcomes. So after studying this module, you shall be able to 1. Understand the atomic perspective of crystal states, where we start understanding things from atomic orbital concept. Second, we will also learn about another method of working out the electron eigenstates and the eigenenergies in a crystal, and this method is called a tight binding method. Then we will also learn about the tight binding approximation for some other cases also, like the degenerate levels, lattices with bases. And finally, you will learn about the properties of narrow bands, deep levels, and how the ions are formed. In the previous module, we learned about some important and interesting features of the quantum states of electrons in crystals. Our starting point was the free electron waves there, and we examined the effect of periodic potential on such wave functions. The potential was taken to be weak so that we could use perturbative theory to treat it. Now, as mentioned in this treatment, it is very useful and practical for conduction electrons in metals, which in Drude's rather successful picture are regarded as a free electron gas. In this module, we adopt a somewhat opposite perspective, starting with atomic orbitals, where again simple arguments provide a complementary understanding of this problem. Atomic perspective of crystal states. We start here with the atomic orbitals. Here we consider changes in atomic states as atoms come close to each other to form the solid. We imagine a collection of atoms in a lattice with its lattice constants A much larger than R0, where R0 is the radius of the valence electrons. We now consider what happens as the lattice constant is reduced. The form of the potential due to the nuclei along a certain line at two distances is such that at larger distance we have a series of more or less non-overlapping wells. As atoms come closer, the wells overlap and potential changes, particularly in the intervening space as it is considerably lowered. At the larger lattice constant, overlap of the atomic potential is negligible, and atoms can be treated as isolated, each with its atomic levels, which are common to all of them. As atoms come closer, electrons in a given atom are drawn by its neighbors and their wave functions begins to spread. These wave functions must obey the Bloch theorem, as that is a general result of the periodic nature of the lattice. Bloch's theorem gives equal weight to the wave function in all the cells of the crystal, which results in wave functions that are spread all over the crystal with equal probability around each atom. The extent to which a given state is affected depends on its size. For simplicity, let us consider the example of sodium atoms. The 1s state, which has a small extent and which lies in the deepest part of the potential, is not much affected, as its overlap with the potential of the neighbors is minimal, even at the lattice constant where metal is formed. For the higher atomic states, overlap with the outside potential increases, and so does the change in their wave functions. For the 3s wave function, changes are most drastic, as its energy levels lie in the range where the potential is more or less uniform. This results in wave functions which are nearly plane waves with small modulations. Based on these considerations, the following qualitative description of energy levels emerges. Let us focus on one atomic level with quantum numbers N, L, M. For large enough lattice constant, where atoms can be regarded as isolated, the level in each atom has an identical value. So we have an n-fold degeneracy. As atoms come closer, the wave functions spread and this degeneracy is lifted, as will be shown in the next few slides. This results in a band of energies containing closely spaced n levels. The width of the energy band depends on the overlap of the wave functions between neighboring atoms. It thus increases in general with the increase of atomic energy level. For degenerate atomic levels, the band states are formed by their linear combinations, and band energies are not degenerate in general. For lower levels, the bands are narrow and have gaps as in atomic levels. This picture provides a natural explanation of energy bands in crystals. They just originate from the discrete energy levels of atoms constituting the crystal. For higher levels, the bands spread to cover several atomic levels, and it is not useful to regard a particular level as their progenitor. The method being described here is useful for only narrow bands. In this way, it is complementary to the weak potential analysis, which is suitable to free particle-like bands in conduction band of solid. The tight banding method is based on the observation that the potential in the intervening region between atoms is much weaker than those in the regions of atomic cores. As a result, the wave function has larger amplitude in the core region compared to the intervening region. This particularly affects the narrow bands originating from deeper atomic levels. Let us elaborate these ideas first for a crystal with one atom per cell. Due to translational symmetry, however, no one atom is preferred over the others, and Bloch theorem must be obeyed. We construct a linear combination of functions which are localized around each atom in the following way. Let us take this wave function xi k as a function of r, which is equal to 1 by root of n summation over all the vectors r e raised to power I k dot r multiplied by the function phi r minus r. So this phi r minus r is denotes a localized orbital around the lattice point r. The coefficients e raised to power I k dot r in this linear combination have same magnitude for all the atoms and are chosen to satisfy the Bloch theorem as described. So that is xi k r plus r l is equal to 1 by root n summation over r e raised to power I k dot r into phi r minus r plus r l. So rewrite this equal to 1 by root n summation over r2 e raised to power I k dot r1 plus r2, and now we have phi r minus r2, which is equal to e raised to power I k dot rl multiplied by xi k r, where in the second line the summation variable is changed, that r2 vector is equal to r1 vector minus the r vector. So our next step is determining this phi r minus r. From the physical picture that we have developed up till now, we expect phi r minus r to be one of the atomic eigenstates. However, due to change of potential in the crystal, it should be allowed to be different. Due to its localized nature, it is useful to expand it into atomic states around the vector capital R. So, phi small r minus capital R is equal to summation over m Cm phi m r minus r, where this phi m are atomic orbitals for the atom at point R. Now our task is reduced to finding the coefficients Cm. The physical picture suggests that for each band, one of the Cm's is large, providing its association with an atomic level, while others provide correction. Taking this to be a good choice for the wave function, we adopt a variational procedure to determine the various Cm's. The energy expectation value is Ek is equal to the expectation value of the Hamiltonian H with respect to the wave function divided by the normalization of the wave function. We first evaluate the denominator as it is easy. So as you can see that the expectation of these two wave functions is quite straightforward, and eventually what we get is a summation over n and m Cn star, we start with the bracket, delta nm plus summation over the vector r, where r vector r is not equal to 0, beta nm e raised to power minus I k dot r whole multiplied by Cm. Here we use the orthonormality of the atomic wave functions on the same side and define the overlap integrals as below. That is the integration of phi n star phi m for the entire space is equal to delta nm, and again the integration over the entire space phi n star phi m star. Now remember that here the two indices is now not the same as in the earlier case, so it is one is I, the other is j. This leads to beta nm rj minus ri. To compute the expectation value of the Hamiltonian, we first evaluate h phi m, splitting it in two parts, an atomic part at site Ri and the rest of the potential. So this means that the Hamiltonian H multiplied by phi m is written and given like on the right hand side, that is the kinetic energy part, P square by 2m plus the potential V r minus Ri plus the potential J, which is not equal to I, the rest of the potential due to the other ions, V r minus Rj phi m. So now what we do is that we calculate now the remaining part, that is the expectation value of the Hamiltonian with respect to this wave function. So again this is quite straightforward, 1 by n summation of I and j, again a summation over m and n, Cn star e raised to power minus k dot Rj minus Ri, integration over the entire volume. Then we have a phi n star h phi m and Cm finally. So as you can see that using the previous results, we can straightforwardly write this as summation over nm Cn star start bracket gamma nm 0 plus summation over all the vectors r which is not equal to 0 gamma nm r e raised to power minus I k dot r multiplied by Cm, where this gamma nm is the short form for this negative of the volume integral of phi n star delta Vi phi m. Now what was derived earlier, now these are the standard linear eigenvalue equations for CMs. Once the atomic levels and the lattice structure are known, all parameters occurring in these equations can be determined. Energy eigenvalues for each value of k can now be obtained from the corresponding determinant. The number of eigenvalues is equal to the size of the determinant, which is equal to the number of atomic orbitals used in the expansion of the function phi r. The size is chosen by physical and numerical considerations. These eigenvalues form bands of closely spaced levels as the value of k is varied over the Brillouin zone of the lattice, giving us n levels in each band. This what we have described is a very general procedure. So we have to make some further approximations so to get a feeling about the results that we can obtain by this. The net conclusion that we can draw from our discussions of the previous slides is that once the atomic orbitals, atomic levels and the lattice structure is known, all parameters occurring in these equations can be determined. Energy eigenvalues for each value of k vector can now be obtained from the corresponding determinant. The number of eigenvalues is equal to the size of the determinant, which is equal to the number of atomic orbitals used in the expansion of the function phi. The size is chosen by physical and numerical considerations. These eigenvalues form bands of closely spaced levels as the value of k is varied over the Brillouin zone of the lattice, giving us n levels in each band. Now we discuss the non-degenerate levels. Now as discussed before, what we have been suggested is that the bands of eigenvalues are clustered around the atomic eigenvalues. For the eigenfunctions in a certain band around the level OL, one expects the coefficient CL to be dominant. Let us consider the case of a non-degenerate level, say an S level. As a first level approximation, we neglect all other coefficients except Cs. With just one coefficient, the energy is trivially obtained as ESK is equal to OS minus gamma SO plus summation R not equal to 0 gamma S R e raised to power minus I k dot R divided by 1 plus summation over all the vectors R beta S e raised to power minus I kappa dot R. Now several points about the above expression should be noted. First, beta S, which represents the overlap of atomic wave functions from different sites, fall exponentially with the distance between the sites due to the exponential decay of the wave function. The same is true of gamma S. Delta S is the change in the energy of the atomic state in the crystal, and it is taken negative as the additional potential at any site is generally negative with respect to vacuum. Gamma can have both signs, but for S levels, it is easily seen to be negative. The above considerations can simplify parameters. We neglect beta S in comparison to unity, and being in the denominator, it provides a higher order correction. We also assume that gamma S is substantial only between the nearest neighbors for the lattice. Further simplifications follow from the symmetries of the lattice. The inversion symmetry imposes the condition that delta Vi of minus R is equal to delta Vi of positive R. For S-like atomic states which are spherically symmetric, gamma S of minus R is equal to gamma S of R. Let us consider bands for some simple lattices under the previous approximations. For a one-dimensional lattice, we have ES is equal to OS minus gamma S minus 2 times gamma cos of Ka. Now here, let me recollect that OS is basically the kinetic energy. For a simple cubic lattice, 6 nearest neighbors vectors are the vector delta, small delta is equal to A plus minus 1 0 0, A 0 plus minus 1 0, and A 0 0 plus minus 1. The cubic symmetry guarantees that gamma S as a function of the vector delta is equal to gamma S. This yields for the band the following equation for ES. Now note here that this equation is different from the previous equation in the following way, that the third part of this equation, minus 2 gamma S, in the earlier case was minus 2 gamma into cos Ka. But here now we have got minus 2 gamma S multiplied by cos Kxa plus cos Kya plus cos Kza. Finally, for a BCC lattice, the nearest neighbor vectors are the small delta vector is equal to plus minus 1 comma plus minus 1 comma plus minus 1 into A divided by 2. Again, due to cubic symmetry, all gamma S as a function of delta are equal. Now, as before, so what we assume is that due to cubic symmetry, all gamma S as a function of small delta is equal to gamma S. The resulting band is simply given by ES as a function of the K vector is equal to OS minus gamma S 0 minus 2 gamma S multiplied by, in a large bracket, cos Kxa plus cos Kya plus cos Kza divided by 2 plus cos of Kxa minus Kya plus Kza by 2 plus cos Kxa plus Kya minus Kza by 2 plus cos Kxa minus Kya minus Kza by 2. Now evaluating this and simplifying, you can simply write down this as ES is equal to OS minus gamma SO minus 8 times gamma S cos Kxa by 2 cos Kya by 2 cos Kza by 2. We first note that the energy range or the width of this band in this approximation is 2z gamma S, where the z is the number of nearest neighbors. Since gamma S is basically determined by the ratio of the wave function decay length and the lattice constant, it increases with the quantum number n and decreases with the lattice constant. The addition of the neglected parameter does not change these qualitative features. Further, note that for small k, all these expressions yield Es is equal to Os minus gamma S0 minus Z gamma S plus gamma S into Ka whole square. Thus, for K approximately equal to 0, the energy levels have the free electron-like dispersion, that is wave vector dependence. This can be rationalized in the following way. For wavelengths K inverse much more than A, the electron does not sense the lattice structure and has dispersion appropriate for the continuum. Now we treat the tight binding approximation for some other cases. So let's take the case of the degenerate levels. We consider bands formed by a degenerate atomic level like a P or a D level. One can use the general formalism that we had described previously, but the minimum number of states one has to keep it all the L-fold degenerate states with wave functions phi m. Here no one state can be special, and in the potential of the solid approximate combination of states appear which conform to the point symmetry of the solid. Then we expect that a certain linear combination of the states would replace the local orbitals. As an example, consider the case of p levels in a simple cubic lattice. For an atom, we write these levels in terms of spherical harmonics as described by this equation. However, recall that the spherical harmonic R y L plus minus 1 is proportional to x plus iy. It's complex. And R of the spherical harmonic y L0 is proportional to z. So we can equally well take these degenerate states to be x up, y up and z up to be collectively denoted by xi alpha. Alpha is x or y or z, that is along the three axes. They are no longer eigenstates of the angular momentum, but that does not matter as the crystal potential does not have the spherical symmetry. For crystals with cubic symmetry, the above linear combinations are very useful as we see below. Now we write the p level tight binding wave function in terms of xi alpha as xi k 1 is equal to 1 by 2n summation over the vectors r e raised to power iota k dot r, again summation over alpha c alpha xi alpha. Various constants occurring in the eigenvalue equations can now be evaluated considering the following expression for gamma alpha beta. Now remember that this integral is 0 unless alpha is equal to beta. Furthermore, due to cubic symmetry of all three directions are equivalent, making gamma alpha beta is equal to delta alpha beta to gamma p. Similarly, beta and other matrices are also diagonal with our choice of basis. This leads to three degenerate bands which to leading orders are E alpha is OP minus gamma p of k. If we had used spherical harmonics or any other linear combination, the same result would be achieved, but with a little more effort as the matrices gamma beta would not be diagonal. In general, one obtains L k-dependent eigenvalues. However, in several problems, levels other than just degenerate levels need to be included. This happens when these other levels are also close in energy. For example, in some 3D series transition metals, 3D and 4s levels come close, so accurate description of 3D bands which are still narrow requires inclusion of 4s states. Similarly, in group 4, some semiconductors like germanium, S and P levels need to be included for valence states. The mixing of atomic levels in solid is referred to as hybridization. Lattice with basis. Next we consider crystals which have more than one atom per cell. First consider the case of two atoms. The above analysis suggests that we take linear combination of orbitals from each atom and then construct block states in a similar manner. So psi k is equal to 1 by root n 2n summation over the vector r e raised to power I k dot r, and then in the big square brackets we have the following, that is summation over n an phi n plus bn phi n, while including a large number of states from each atom and constructing general wave functions is straightforward. Developing useful insights and simplifying analysis to practical levels requires some chemical and physical considerations. For some molecular crystals, there is a strong overlap of wave functions between the atoms. Here it is more physical to take molecular levels as the basis for expanding the wave function in each cell. For other compounds, the wave function overlaps between constituents change considerably in solids. For them, it is more appropriate to choose a few orbitals from each atom judiciously and use the wave function of the above form. Properties and role of narrow bands, that is deep levels and formation of ions. The Bloch theorem asserts that all single electron levels in a crystal are extended. This applies to even those originating from deep levels like 1s. Although these have very narrow bands, one can construct a wave packet of these states and in a similar manner argue that the group velocity of the packet is Vk, which is equal to 1 by h cross del of k of E. That is, like in the case of one dimension, Vx would be equal to 2 gamma s a by h cross sine kx a, or equal to Ba divided by z divided by h cross sine kx a, where B denotes the width of the band. This argument, which is more generally true, shows that the velocity of the particle is proportional to the bandwidth. Thus, all states have mobility, though it can be very small for narrow bands. The smallness comes from the parameter gamma, which can be interpreted as quantum amplitude for tunneling from one atom to its neighbor. A physical way to view these states is that the electrons are for most time in the core region of the atoms, but tunnel to the neighbors occasionally. So, from our discussion in the previous slide, there is a contradiction actually, that when we say that like electrons in deep lying atomic levels are part of the ions and are therefore attached to the single atom. Now, what basically is the dilemma here, the contradiction? Basically this means that this narrow band structure which we have discussed, this clearly indicates that these electrons which are lying deep, they are not really very part of those ions. They could be slightly delocalized, not the one, like not really very delocalized, but they could sort of go out. So in order to understand this requires considerations which go beyond the physics of single particle states. Remember that if we have single particle states, certainly this is true that these electrons in deep lying atomic levels are part of the ions. But we are dealing with electrons which are fermions, and this is no longer true. In a solid, there are obviously a huge number of electrons which affects physics in two broad ways. One, to the Fermi-Dirac statistics, which forbids the occupation of two electrons on the same level. Okay, so I understand this, that the Fermi-Dirac, we have electrons as fermions, they follow the Fermi-Dirac statistics, and two electrons on the same level, it's not possible. So naturally, if there is already one existing electron, the other one, it's not so easy for it to come to the same level. Then the second part is through repulsive electron-electron interaction. So both of these 1 and 2 which I have just said does not make the electrons in the deep lying atomic levels as part of the ions, and that's where the contradiction is, and this is how we understand this contradiction. Consider a band arising from a deep lying atomic level which is fully occupied in all the atoms of the crystal. Imagine an electron in this level to tunnel from one atom to the same level on its neighbor, which easily happens in an empty lattice. But here this process is forbidden due to Pauli's principle. In fact, a hop requires a large energy as it may have to jump to a much higher level. This is not possible if the energy gap to empty states is more than the width of the band, as the electron has to tunnel successively through the crystal to form band states. This argument can be extended to all filled bands. This means that the electrons in all low-lying filled levels remain tied to one atom, forming ions. Narrow valence bands. It is not just deeper levels that form narrow bands. There are many cases where valence bands are also narrow. Consider, for example, the case of a solid formed by the compound NiO. The p levels of O have lower energy than the 3d and the 4s electrons of Ni. So a simple picture is to view the solid as formed from the ions Ni++ and O negative. The p electrons of O form a filled band lying below the band formed by the d electrons of Ni. Due to structure and interatomic distances, d electrons have small overlaps and form a narrow valence band. For such bands, electron-electron interactions play a very important role. In fact, developments in solid-state physics in the last couple of decades have thrown up a large number of cases where the physics is governed by narrow bands. An entirely new era has come up known as the narrowband materials, or alternately as strongly correlated systems. Foremost example is the high Tc superconductors, which are layered oxide containing several elements. Here, the action happens in the narrow valence band formed in the copper oxide planes. For example, in the case of La2 Sr L-X BaX Cu O4. The study in this area is very challenging as for narrow bands, electron-electron interactions govern important physics. We will discuss some of these exciting developments in the later modules after we have developed some prerequisite ideas. Okay, so students, let us summarize what we have learned in this module. In this module, you studied 1. About the time binding approximation to work out the electron eigenstates and the eigenenergies in a crystal. So we started with atomic solutions and examined how these wave functions change as atoms are brought together to form a solid. This method provides a complementary perspective on the formation of energy bands in solids. Second, this method provides a good picture for discussing narrow energy bands that originate from low-lying atomic states, whereas the weak potential approximation serves well for describing conduction bands that are close to plane waves. Bands formed by a degenerate atomic level like p or d levels we have learned. We also studied the tight binding approximation for the crystals having more than one atom per cell. Now also that we learned was that the Bloch theorem applies even to those electrons levels which originate from deep levels like the 1s. Also a physical picture arises stating that the electrons are for most time in the core regions of one of the atoms but tunnel to their neighbors occasionally. And finally, we also learn about the role of valence bands which form the narrow bands apart from the deeper levels. Thank you.